We present a CQT CycleGAN WaveNet pipeline that performs timbre transfer on raw audio. Timbre characterizes the sound of an instrument. Modeling timbre is hard, and it has been referred to as the psychoacoustician's multidimensional wastebasket category for everything that cannot be labeled pitch or loudness. Modeling and manipulating timbre electronically carries importance for musicians who wish to experiment with different sounds or compose for multiple instruments. In our first attempt at solving this problem, we began by converting audio waveforms to spectrograms using the short-time Fourier transform, also known as STFT. We then trained a CycleGAN to convert STFT spectrograms of the source instrument into STFT spectrograms of the target instrument. This required only collections of unrelated recordings of each instrument. The audio waveform of the target instrument was then reconstructed by the Griffin-Lim algorithm from the spectrogram. Here's an example result of this initial process. As you can hear, the audio quality isn't that great, and the pitch is not preserved. To address this, we replaced the STFT with a constant Q transform representation, also known as CQT. Because the CQT uses a log frequency representation, it's natural for convolutional architectures because it provides equivariance to pitch. We then train a CycleGAN to convert CQT spectrograms of the source instrument to those of the target instrument. Unfortunately, unlike the STFT, the CQT doesn't have an easy method to recover a waveform. Instead, we trained a WaveNet synthesizer that's conditioned on CQTs to produce the corresponding high-quality audio. We name our pipeline TimbreTron in honor of the tachotron system for speech synthesis. We can visualize the outputs of TimbreTron using the rainbowgram, a variant of the CQT which uses color to encode time derivatives of phase. This highlights subtle timbral features which are otherwise not visible in a magnitude CQT. Training a WaveNet for CQT also has the advantage of letting us manipulate the speed of the audio. This can be done simply by sampling fewer or more values per spectrogram window. If you did not hear some of the bumbling in this musical sample, let's try listening to the slowed down version. How about now? Somebody needs to practice more. On the other hand, there's no better way to cover up mistakes than to go even faster. Let's speed this up. Because of its equivariance property, the CQT representation also lets us manipulate pitch by simply shifting the spectrogram vertically. Finally, we now present audio samples from our full CQT CycleGAN WaveNet pipeline.